Okay, welcome to, I think, lecture 24. Today we'll continue looking at bifurcations. In fact, I just want to look a little bit more carefully at the homoclinic bifurcation that we looked at the last time, and just give you an idea of what the exactly how to quantify when basically the limit cycle gets destroyed. So if you look at this example that we were looking at, where you have x dot equals to y and y dot equals to a, which is the parameter we're going to vary, y plus x minus x squared plus xy, the first step, obviously, which I actually didn't do last time, is you look for where all the fixed points are, y equals to 0, and then therefore at x equals to either plus or minus 1. You do the linear stability analysis around all the fixed points. Okay, so you work out the Jacobian, and then at each fixed point you find out what the Jacobian is at that fixed point. So here we have at the origin, it's this matrix that has a determinant of minus 1, right? And so we immediately know it's a saddle. At the second place, at the 0, 1, we have this Jacobian, and we can work out that its determinant is positive and its trace is given here. So we immediately know that at 0, 1 we have a fixed point which is stable if A is less than minus 1, and unstable if A is greater than minus 1. Okay. So, and we can also work out what the eigenvalues are, and there they are explicitly in terms of A. And the reason for doing this is that in order to have a limit cycle, we want to know what parameters we want to play in, and the limit cycle can be found by simply looking at the parameters that are of interest can simply be found by looking at the eigenvalues. So, for example, here, if A is less than minus 3, we have a stable node. If A goes from minus 3 to 1, we have minus 1, we have an unstable spiral. So we've gone from stable node to unstable to stable spiral. If A equals to 1, equals to minus 1, we have a center, remember. And the moment A gets bigger than minus 1, we have an unstable spiral over here. And if it gets bigger than 1, we have an unstable node. Okay, so those were the parameters in A, that the initial take or the initial guess of where the limit cycle would be is you at least require an unstable spiral or unstable node. So the place I went looking for a limit cycle was where A was bigger than minus 1. So what I did in order to actually plot those plots I gave on the blackboard, I made a numerical exploration. And remember, we had this very magical number, mu c, the critical point at which I set the Hopf bifurcation took place. The way I found it was as follows. I plotted one case numerically, and I chose minus 1 because that's where I know the spiral goes unstable, and therefore you're at least expecting to have a small little limit cycle around that Hopf bifurcation. Okay, so there we have it. And the thing that I chose to plot, the trajectories I chose to plot, all came from the saddle, right? The saddle plays a very, very important role in your homoclinic bifurcation. So I chose first to plot the trajectories from the saddle. I basically worked out the eigendirections of the saddle, went out a little bit on that eigendirection, and then let the MATLAB solve the differential equation. So what I had there is in what I call the unstable manifold, the direction with a positive eigenvalue, I saw the trajectory depart. In this side, I did the same thing. I went a little bit out on the eigendirection, like the 0, 0, 1 in that eigendirection. And then I integrated the equations, and I once again had my unstable manifold go out, bend back round, and then I integrated, and it bent in, and eventually it went in all the way, it spiraled in very, very, very slowly to a limit cycle over there, which is where I expected the Hopf bifurcation. The same way, if I look at my stable manifold, that's the arrows that go into the saddle. I basically went out here a little bit and then integrated backward in time, like I showed you on that example with Python. Okay, and I could make the trajectory. So in some sense, anything coming in will go round and eventually end up at the saddle. And so this purple thing actually makes a capturing region for the stable manifold, right? Remember, it's impossible to pass a trajectory. And so this purple stable manifold over here that approaches the saddle captures the region where the limit cycle has to take place. Okay, so the next thing I was like, okay, now I have a limit cycle and I have a saddle. I have therefore got the possibility of having a homoclinic bifurcation where my limit cycle gets bigger and bigger and it collides with the saddle. So what I did then is I increased A, right? Because remember, when you have a Hopf bifurcation over here, in other words, when this limit cycle is born, when your fixed point goes unstable, you expect the limit cycle to start small around the fixed point and then to grow as you increase the parameter. So the natural way for me to go looking is to increase A. And so if I have A equals to minus 0.093, so there's no actual guide for this except that I expect A to be less than 1. So I increased it slowly, and what I saw happening is that I once again plotted my stable manifold. Okay, I saw that the limit cycle, instead of spiraling in quite rapidly to a small circle, it very quickly approached this much larger limit cycle. And what I was also able to do is plot my unstable manifold, and there it goes. Okay, so once again you have the unstable manifold enclosing this limit cycle that is now getting much closer to it. Okay, so I still have not found the bifurcation point. What I do now is once again I increase A, because I can see that this thing is going to expand and eventually hit this purple boundary, and so I simply have to find the parameter at which that thing occurs. Okay, so here we go. If I again increase A to the point at which the homoclinic bifurcation takes place, and this value I found experimentally. I basically took A, integrated the equation, and the moment I took my, and there's my, unstable manifold, the moment I could integrate from my unstable manifold, and I went round and I went back to this point, rather than hitting a limit cycle over here, I knew I was at my bifurcation. So I take very small steps in A, I look what A does after a certain period of time. If A remains bigger than X equals to 0, if X remains bigger than 0, then I know I've got a limit cycle. The moment X actually in the integration crosses 0, I stop the integration and I start looking closely to that point, because that's where my homoclinic bifurcation is going to take place. Okay. And so if you do the stable manifold, you can actually integrate it backwards and you can see it's exactly the same orbit. If you look at an orbit over here, you'll find that it'll spiral out and go onto this orbit that has the infinite period of the that's associated with the homoclinic bifurcation. Okay, so it's going to spiral out and eventually just basically get stuck at the saddle point. And then this is basically, to answer Sapizio's question, you go on, and just to make sure you have the right homoclinic bifurcation, if you now increase AC, and once again you, if you increase A just even a little bit, you'll find that your unstable manifold, you no longer have this closed loop that is so typical of the Hopf bifurcation, but rather this thing goes to negative infinity X always. And so you know you've passed the homoclinic bifurcation point. Okay. And so once again, if you plot the stable manifold, you have that very nice picture. So the brief summary is the unstable manifold is key. In other words, this blue curve is key to determining when the homoclinic bifurcation takes place. And what basically is, or the basic criterion is, it leaves the origin along the eigendirections, so over here. If it loops back and doesn't return to the origin, so it gets stuck there, you have a limit cycle. If it loops back and goes exactly to the origin where it started, returns to the saddle, you're at your homoclinic bifurcation point. But if it loops back and then goes to negative infinity, you know you've passed it. Okay, so it either returns to the origin, it veers off to a fixed point, or it veers off to infinity, and all you have to do is to find the points roughly between 1 and 3. In other words, where it comes to the fixed point at, where it goes round the fixed point and returns to the origin. Okay. So that's the criterion. Homoclinic bifurcations usually find just numerically, because there are very few examples that you can actually do it analytically, but they play a very, very important role in a number of things, and we'll look at an example in what follows. The only thing I want to do is make a summary of how you identify bifurcations physically, okay? The way we identify bifurcations physically is by means of scaling laws. If you see a problem and you have to start guessing the equations that govern it, and you see certain scaling laws, you need to know that you at least have to have a model that includes that bifurcation. This thing of the name characteristic scaling laws is not an accident. You see it in physics, you see it in phase transitions, and at the most fundamental level, a phase transition in physics is a bifurcation. Okay, it's a parameter you've changed, be it the temperature or whatever, that changes the actual dynamical state of your system. So in physics, it has sort of an elevated position, but it is in fact a bifurcation. Okay, and these laws govern the amplitude, the period of the limit cycle when they are born or when they are destroyed. Okay, and I'm just going to summarize it for you. We've derived some. I don't expect you to derive the ones that we have not done, but I do want to give you the summary so that if ever you have a problem and you're looking for which models at least to start guessing at, this is the thing where you're going to sort of start. Okay, so basically the scaling laws govern the amplitude and period of the limit cycle as the bifurcation is approached, and what we're going to do is call mu, which is basically A in the previous example, a dimensionless measure of the distance from the bifurcation. So remember in the sniper bifurcation we had that omega, and then mu was actually omega minus omega's critical value. Typically that's what mu is. Okay. Then the scaling laws for the bifurcation of the cycles basically in 2 dimensions are listed below. So I'm going to give them to you and then just discuss them briefly. So it also just reminds you of the names of what these bifurcation of limit cycles actually are. Okay, so remember we had the supercritical Hopf bifurcation where the fixed point went unstable to a limit cycle. Okay, its typical characteristic is that its amplitude of the limit cycle grows from 0 like a square root. That's always true of your Hopf bifurcation. Okay, what's also true is that the period, it's born with a known period, and that known period is the imaginary part of the spire of the eigenvalue when your fixed point goes unstable. Okay, so this order 1 basically refers to the imaginary part of your eigenvalue. The second one that we looked at, that we saw in that example that came from the quartic potential, where we had hysteresis, was basically the saddle node bifurcation of cycles, where you basically give birth to a stable and an unstable limit cycle at the same time. They can be born at any amplitude. So typically the amplitude has got a finite value, and also they are born at a fixed period, right? And typically the period is the period of the limit cycle over there. So this is what characterizes a saddle node bifurcation or cycles. Okay, the sniper or the infinite period bifurcation, remember, was we had that fixed limit cycle, we had a fixed point on the limit cycle, it sort of disappeared, and then you had this infinite period limit cycle starting, and we actually derived that the period of the limit cycle is scaled like mu equals -1/2. We derived it in the special case of our example, and then I argued most generally that this is always true, because the thing that sets the time scale of the period is how long the ghost influences the limit cycle near the point where the fixed point was. Okay, that limit cycle is also born with a finite amplitude. This homoclinic limit cycle is another bifurcation. Once again, the homoclinic cycle is born with a finite amplitude. The amplitude is basically as big as the initial homoclinic orbit, and you can see that the period of the limit cycle goes like the ln of mu. Okay, I didn't derive this. I'll tell you how to derive it, but I'm not going to do it. But anyway, this scaling, if you conduct an experiment and you change a knob and you see the limit cycle being born, and you see the period of the limit cycle changing from infinity to something smaller, and it goes like 1 over the square root of mu, then you know it's a sniper bifurcation, infinite period bifurcation. If it scales like the ln of mu, then you know it's a homoclinic bifurcation. Okay, so there's two checks. Well, either you can know enough about the phase diagram to know you have a saddle point, or you can actually measure how your limit cycle changes with the knob you're changing experimentally. Okay, the period over here was basically derived by estimating how long it's going to take to pass the saddle point. Okay, so that's the criterion that determines what the period of the limit cycle is. You simply go to the slowest point, which is near the fixed point in the saddle. You work out how long it's going to stay there, and that's a good estimate for what determines the length of the limit cycle. Okay. So that's it. The content of your test on... Yes? Nee, is 2. Ja. Ja.
Ek kry al die netjie ons net kyk met 'n podium net geskryf word in die podium.
Ja.
Wag net vir hom, dan kan ons net vinnig wil kyk as jy klaar is, of hoe laat maak jy dit klaar?
So oor 'n halfuur.
Ja, dis nie.
Ek rekord die lecture vir ander mense, so dis 'n bietjie van 'n issue om dit nou te stop. So what I'm going to do next, okay, so your test is up until the end of 8.4, okay, the chapter 8.4, up until before the Josephson junction. So I expect you to know what all the bifurcations are, but the special example of the Josephson junction is not yet necessary to explore. Okay. What I am going to do is I'm going to start giving the motivation for the Josephson junction before they come and interrupt us to take our computer away. And so what the Josephson junction is, it's maybe one of the biggest advances in physics for permitting us to do quantum computing. Okay. And I want to explain basically where the equations come from before we actually start looking at them. Okay, so it turns out that the equations that the Josephson junctions results is exactly the same equations as a driven pendulum. So whether you view this problem as a Josephson junction or as a driven pendulum, the properties you can observe are the same. The importance of the Josephson junction is just the technological advances it makes possible in the future. Okay, so it's something you'll hear about again. And in fact, last year's Nobel Prize was related to it. Okay. So what this lecture does, it basically combines those two chapters of Strogatz and quite a lot of my experience to make a nice cohesive story. And what the Josephson junction does, it illustrates both a homoclinic bifurcation as well as an infinite period bifurcation. Okay. It In the weak damping limit, it also gives you an example of hysteresis. So there's a lot of physics that actually goes, that you can get out of the dynamical equations that result from the driven pendulum or the result from the Josephson junction. Okay, to tell you what a Josephson junction is, it's a superconducting device. Okay, what makes it unusual is it permits us to reach incredibly high frequencies. So, and that permits us to make switches that are much, much faster than what we find in any modern computer. So you can imagine the jump in computing that will actually go up if we actually are using these devices. Okay, so it allows you to switch very rapidly at a time of 10 to the 11 cycles per second, which is a huge number. Okay, it illustrates quantum mechanics on a macroscopic scale, and you'll see why now. And the basic idea is you have two superconductors, A and B. Historically, they were basically made out of niobium. In order to get them to be superconducting, just as the superfluid, you have to cool them down a lot, historically, until last year. And what we do is you place the two of them alongside each other, and in between, you put something that is not a superconductor, okay? And the amazing thing is there was a prediction that you could still pass current through here without having a voltage across it. So the thing that we use to, what makes a superconductor at least interesting from our perspective, is it's a collective state of all the atoms in this side, and we describe it with a single wave function. The superconductor, the individual atoms, you can't treat them as we do electrons and stuff in normal conductors. You have to view a wave function that collectively describes the whole thing. And the way we do that is we describe the state over here as a wave function, which is just a complex number or a real number times the phase, and another real number times e to the I phi b. Okay, so that's what we're going to use to describe these superconductors. The C is what they call a weak connection. It's typically made of something else like aluminum oxide. Okay, it's very, very small. These things are manufactured in nanofabrication laboratories that many of the universities in America have. You simply etch things in. It's a very clever, basically, method of construction. Okay, and it's an insulator. So what happens in a superconductor is we're going to look, is that current can flow between these two with zero voltage over it. Okay, and to be able to describe that, we're going to introduce just a new variable, which I'm going to call phi, which is the differences in phase between these two superconducting states. Okay, so Josephson did this work, or he did the theoretical work in 1962. He was 22 years old. Okay, he was one of these people that had a tremendous insight at a young age. Not to be discouraging to us older fogies that still try and get insights even at an older age, but he had a talent, and he was also at the right place at the right time, and he understood the implications of the equations that he had. Okay, so what he said is he predicted, which is always an amazing thing in science, by looking at the equations, understanding what quantum mechanics does or how it works, he said that it should be possible, okay, to pass a current from between the superconductors, in other words, from A to B, okay, without developing any voltage across the junction. Okay, now if you talk to a person that's normal with electronics, will say, oh, you're doing magic, because that's not possible classically. Okay, it really isn't. Okay, it's like making water run uphill. Okay, if there's a resistance, the flow of, you need a voltage to push it across. And he said no, because of the state that the two superconductors are basically feeling the whole superconducting state of the superconductors on the left in A and B, this is now actually mathematically possible. It's a form of tunneling, okay, which you cannot find in classical physics. Okay, a year later, somebody took him seriously enough, built an experiment. The guys' names were Anderson and Roll, and they proved it. And it took the world another 10 years to catch on the value and the implication of what the work. And these guys together received the Nobel Prize in 1973. Okay, because they realized the impact it would have on the fact that we could actually start building very rapid switches, very rapid ideas of a transistor in different states. Okay, so just if you actually are interested in this, some of the other things you want to look at is that the way they describe the superconductor is the idea of Cooper pairs of electrons. They basically tunnel across the junction, okay, and they have the same phase, okay, and in some sense they form what you call is a coherent state. It's basically the superconductor feeding that superconductor without actually having direct contact. Okay, so it's a coherent state of all the electrons, and you basically make a single macroscopic wave function between the two of the whole device, where you have this bridge where they're actually tunneling across. Okay, a good place to go and look this up is in Feynman's lecture of physics. Okay. The exciting part in 2020 was that the thing that has stopped this very rapid or powerful switch from being incorporated in computers is you have to do a lot of work to actually see them. Right? You have to cool the things down. Superconductors typically work at like helium temperatures minus a few degrees Kelvin. And slowly over history since 1973 or later, they've been increasing the temperature at which a device can be made superconducting. And 2020, they actually managed to achieve it at room temperature, which for the first time actually makes viable building a computer using this type of technology. So it's something to watch as life goes on and people start looking for faster computers. This is definitely something that can arise. Okay. So, I'm scared. Okay, so basically what I'm going to do now is derive the equations, okay, that we'll be solving, and then I'm going to leave the Josephson junction or sort of discussion there. What is interesting is he's fortunate the equations were that of a driven pendulum, because the moment he derived it, he knew a lot of the properties. And people could analyze it very, very carefully. But the application should always be remembered because it's something that's going to influence future technology. Okay, so how it works is we describe a Josephson junction like a little cross. If we connect it to a current source, in other words, a source of electrons, you have the possibility that a superconducting current can flow across the junction, okay? And we're going to call that current IS, which is just IC, that is proportional to the difference in phase between the two superconductors. In other words, if you have superconductor A with a phase phi A and a superconductor B with a phase phi B, there's a relative phase shift between the two superconductors as a result of the insulator in between. And the current that flows is basically sort of supported by that phase difference. Okay? And the amazing thing, as I've said, is there's no voltage jump. Usually, the normal laws of electronics is your current, in order for current to flow across anything that has resistance, you need to have a voltage to drive it. This is not so. Okay? So it basically behaves as if it has zero resistance, but it has this new property of a phase difference. Okay? So what happens is this obviously can't be maintained forever, right? Otherwise we'd have a whole bunch of little superconductors with infinitely large current flowing. We would have solved many things in physics. So what happens is the superconductors, if the current gets bigger, they drift apart. And eventually, once the current gets big enough, which we call the bias current, then it stops, right? A voltage develops across the Josephson junction. In other words, you're going to need a battery to overcome it. So it's basically this property. You can have a current flow, but there's only a limited minimum amount. There's a maximum amount of current that can be permitted to flow across in this way. Okay, and that voltage is basically proportional to, they found experimentally, or Josephson actually derived, phi dot. Okay, so you can actually take this thing I've described and you can rewrite it as an effective electrical circuit of the Josephson junction in parallel with a resistor, in parallel with a capacitor, and with a voltage across it. And the differential equation you write down is simply the parallel, basically addition of currents. The total current is the current flowing through your Josephson junction plus the current flowing through your capacitor plus the current flowing through your resistor. You write down what they are. So this is the normal current equation for your Josephson junction. This is the current equation for your capacitor, and this is the current equation for your resistor, the standard ones from electronics. Okay. And suppose now that the current flowing around the circuit, we've allowed it to reach a steady state, and it's just a constant. Okay, and so we're going to substitute the expression for our potential into this equation and obtain an equation for phi. So we know for the Josephson junction, the current that develops across the Josephson junction is just a whole bunch of constants that come from quantum mechanics times this phase dot. So we put that in, and we're left with the following equation, right? Your IB is equals to IC sine phi times a whole bunch of constants, which multiplies the capacitance, times a whole bunch of constants divided by the resistance times phi dot. And so that's the physical equation. How you get it to the thing of a driven pendulum is do what we always do as mathematicians, we non-dimensionalize. Okay, and remember the recipe I said for non-dimensionalizing is, for my personal one, you try and get rid of the constants in front of the most complicated term because you want to draw a graph of it, you don't need to shift around. Okay, so to do that, I divide by the whole equation by IC. Okay, so I'm going to get sine phi free, which is a great achievement. Okay, and then what I'm going to do is I want to get rid of some of these other constants, so I'm going to introduce a new time, which I haven't yet chosen, but I'm going to choose it to simplify things as much as possible. So to introduce a new time, I note that the derivatives with respect to time are now just dd tau times d tau dt. D tau dt I have, it's just 1 over gamma times dd tau. And the second derivative, I can simply do that twice. I have ddt squared is 1 over gamma squared times dd tau. And now I'm going to indicate derivatives with respect to time, not as a dot, but as a prime over here. And if I do that, then I can transform this equation as follows, right? Remember, I divided through to get sine free, okay? So there I have my sine phi. I have this second derivative. I've added the gamma squared over there. And I've got the 2 primes there. I've got this final one over here. I've added the 1 over gamma that comes with the ddt over there. And now the prerogative, I can still do the final thing, is remember I can choose gamma and I can relabel these derivative basically the things in front of the derivatives. And if I have to exhibit a preference there, the way I do it is to once again try and simplify as much as possible the term in front of the highest derivative. So what I've done first, the nonlinear terms, I try and simplify. I got rid of IC there. Then I'm going to use gamma to simplify this term, and simple I view as 1. Okay, so I'm going to choose a new constant that relabels this one. I'm just going to call it I. I'm going to choose I'm going to choose gamma so that this whole thing is equals to 1, and that tells me that I can choose gamma simply to be the square root of C pi bar over 2 ELIC. And then finally, I'm going to label this whole thing to be a different constant, which I'm going to call alpha. Okay? And to make the thing complete, I have to replace what gamma is into alpha, and I have that. Okay, so I've reduced the number of constants from 1, 2, 3, 4, 5, 6 to 3. Okay, and only 2 of those actually appear in the equation. Okay, so I've gone from 6 to 2 parameters, and this equation is the equation for a driven damped pendulum. So remember when we looked at the pendulum, we had phi double prime is equals to minus psi phi. Okay, then we put in damping, which is the alpha. This driving we didn't yet do, but we'll see the impact of it as we analyze the equations, but this is basically a source term. And so that then gives us the equations we'll be solving or analyzing in detail in the next lecture to actually look at various examples of bifurcations, to also look at why a Josephson junction can actually be used as a switch, because it is totally about hysteresis and bifurcations that makes this such a powerful thing. The tremendously great thing is that there's a physical realization where you can choose these things so that the switch happens basically at 10 to the 11 or slightly less times a minute, which can greatly, if they build a computer, increase its power. Okay, so it's definitely something to watch into the future and to understand how it works. The lecture I'm going to end there. I just actually brought an illustration, okay, to try and further illustrate why the Josephson junction can actually, through collective behavior, just look as though it comes, it flows across the barrier. And the illustration, which I'm going to give you now, it basically comes to the question, is it possible ever for water to flow uphill? What do you say? Huh? You don't think it is? What do you say? Huh? You're not sure. What do you say? You don't know. I mean, have you ever seen water flow uphill? Come. Okay, so there's my jar of water. And suppose I want to get it